Now let's see how we can apply Faraday's law by considering a couple of examples. Let me consider something general first. So we have this loop. It's a planar loop. So this is the circuit. This is your circuit, which is the parameter of the loop here. And there is a magnetic field, a uniform magnetic field that is penetrating here, and it's make an angle theta with the normal. So this dotted line represents the normal to the surface. So this is the angle between the B and dA, or A in this case. Now, the magnetic flux through the loop is this, in this case, BA cosine theta, okay? Because it's a uniform magnetic field and planar loop, so the integral reduces to this. Now, if the induced electromotive force, if this flux is changing, is minus d by dt of the whole thing here, of BA cosine theta, okay? So it is d by, because minus d by d phi by dt. And what is phi? Phi is this, BA cosine theta, okay? So how does this change? Now, so this is the flux. So how does this quantity change with time? There are more than one way of doing it. First, if the magnetic field itself, it's constant in direction, okay, and it is uniform over the whole loop, it doesn't change from a place to a place, but its strength varies with time. So it's first increasing, decreasing, or it was small and then becomes larger, and so on. So if the magnetic field, while spatially uniform, yani it's uniform in space, so it's uniform over the whole, it doesn't vary over the area of the loop, but its magnitude is changing with time, okay? In this case, you will have B varying. This is one way of having the magnetic field changing with time. So if this changes with time, this whole thing will be changing in time, and you will have the flux changing. The other thing is if the area is changing. So if this, for example, was a flexible conductor, then in this case, you can just, stretch it, or you can compress it, so you are changing the area itself, okay? In this case, A will be changing with time, so the flux will be changing. Or if you change the orientation of the area with the magnetic field, okay? So you either change the orientation of the magnetic field, or you change the orientation of the loop. In other words, you are changing theta or cosine theta. In this case, this quantity will be a function of time. So this whole thing will be varying with time, and so the flux in this case will be varying with time. Now, any one of these or a combination of these will lead to a change in the flux. So the change in the flux can be a change in the magnetic field as a function of time, area as a function of time, or the orientation of A and B as a function of time. If it changes as with time, then in this case you will have, in all of these cases, or in any combination of these, you will have a changing flux. And so you will have an induced electromotive force in the loop. So this is a summary of these. Now this is a good checkpoint for you to review and try to find what is the correct answer. Now let's consider a numerical example, okay, where we can numerically find what is the electromotive force and the current even. So we have a coil which has 200 turns of wire. Each turn is a square, okay? So the coil is a square, just like the one that we have seen here, okay? But here this is a rectangle, that one is a square, and its side is 18 centimeter, and it's in a uniform magnetic field that's perpendicular to the plane of the coil, okay? So this magnetic field is turned on. The figure shows the behavior of the magnitude of the magnetic field within time. Now it's perpendicular means theta, the angle between B and A in this case, is pi over is 0. So cosine 0 is 1. Now this is how does the magnetic field varies with time. So in the first 0.8 seconds, the magnetic field changes from 0, increases from 0 to a B maximum, okay, where B maximum is 0.5 Tesla. Then after that, it starts decaying and according to this expression, B maximum e to minus a t. So it's an exponential decay. A is some constant, so which is not specified. Okay, so this is how the magnetic field in the loop varies. The loop or the coil has 200 identical turns. Each one of them is a square of side 18 centimeters. Now, what is the magnitude of the induced electromotive force in the coil between t equals 0 and t equals 0.8 seconds? So when the magnetic field varies from 0 to 0.8 seconds, it varies from 0 to B maximum. What will be the induced electromotive force? I look at the absolute value to get rid of the minus sign in Faraday's law, and it is N. Now, it is the formula is, as you see, minus d by dt. But you know, if you can find over a finite interval, if it's over a finite interval, then you can replace this by delta phi by delta t. Okay, so you replace this by delta BA over delta t. Note that I have done cosine theta here because cosine theta is 1 in this case, because the field is always perpendicular to the area. So it's BA. Okay, now A, the area is constant, it's not varying. So you take A outside. Of course, I introduce N here because I have 200 copies of the same coil, and you have delta B by delta T, okay, which is how does the how does the magnetic field change over the finite interval. Now, this is the area is just D square, and this is B final minus B initial over delta T. Because it's changing linearly, then you can replace this by delta B. B final is 0.8, B initial is 0, and delta T is 0.8, as you can see from here. So if you calculate these, then this is 4 volts. So here the induced electromotive force during these 0.8 seconds, okay, is 4 volts. It's constant because the change is linear, actually, in this case. It's not a function of time because the change is linear. Actually, you could do something else. You could still have d phi by dt, but you by noting that in this case, what will be, sorry, you could write this function. You could write the function for the time variation. What is this? Well, this is a straight line. It has a slope of 0.5 because, you know, here you have 0.5 you have 0.5 and 0.8, here 0, 0. So the slope will be 0.5 divided by 0.8 multiplied by t. Okay, so the equation of this line, b as a function of t, will be 0.5 divided by 0.8 multiplied by t in this case. And when you take its derivative in d phi by dt rather than dB by dt, you will get the same, exactly the same thing. You will get the slope, okay, which is this. And it's a constant. Now, what's the magnitude of the induced electromotive force in the coil after t equals 0.8 seconds? Now, after t equals 0.8 seconds, the field is dropping exponentially. And in this case, you cannot say delta phi by delta t because it's not changing linearly. So again, you see a d by dt of this expression, which is the flux. This is the magnetic field as a function of time multiplied by A. A is constant. You take it outside. B maximum is constant, and it becomes the derivative of this exponent. The derivative of this exponent is just, you know, minus A, the same function. So, and you have a minus sign. You can take the absolute value all the way. So it is this expression. So as you can see here, now E is not a constant. Now D is known. This is 200. This is 0.18 square. B is 0.5. A is some constant. So this whole thing is a constant, but this quantity here is a function of time. So the electromotive force here is not a constant. In the first case, it was just 4 volts. Okay? So during the whole time, you had a constant electromotive force of 4 volts between 0 and 0.8 seconds. Here, you have a time varying electromotive force. Okay? So as time passes, the electromotive force is changing with time. Yani the current also is changing with time. It's decreasing, actually, with time. So that's it. When you calculate it, it is this. So here it depends upon A. What is this constant A? We are keeping it general here. What is the magnitude of the current, well, the current is in the first 0.8 second. In the first 0.8 second, we have a constant electromotive force. You divide the electromotive force by the resistance of the coil, which is 2 ohm. It's given as 2 ohm, and then you can find what is the current, which is 2 amperes. So a steady current of 2 amperes will pass through that coil in the first between 0 and 0.8 second. After that, this current will start to decrease. Why? Because the electromotive force after 0.8 second will start decreasing with time. Okay? At later times, it becomes smaller and smaller, and so the current also will drop.